To apply the lessons of chaos to complex systems, mathematicians draw pictures of the behavior. As we watch this circle distort into ever new, curious shapes, it's hard to believe that they're all, even the original circle, computer representations of that innocuous equation, x squared plus c, the equation that gave us video feedback. Simple rules, it seems, can produce fiendishly complicated results. There is complexity here that was implied but never realized by Newton, glimpsed but never resolved by Poincaré. But this is only part of a much greater object. The icon of chaos, its mascot perhaps, is this strange mathematical creature. It has been derived from the simplest of equations, and yet it has turned out to be the most complicated creation in the mathematical universe. Using the computer as our microscope to travel into the valleys and peaks of this extraordinary object, known as the Mandelbrot set, we see literally infinite complexity, however deeply we probe. And that turns out to be one of the hallmarks of both chaos and nature. This unique and paradoxical mathematical marvel is a single image comprising an infinite universe of numbers. Every shimmering speck of color in each spiral and tail is itself a coded key to other unseen mathematical creatures, other new galaxies of color and form. This is the Mandelbrot set. It lives on the frontier of a new geometry, fractal geometry.
The basic elements of the language of fractal geometry were known to mathematicians about 50 years ago. But at that time, they were considered to be mathematical monsters, objects only useful to discuss the limit of certain theories, but nothing basic in nature. And I think that's the true merit of Mandelbrot, to have pointed out to us and to convince us that indeed these monsters are the right things to describe nature.
The fractal is a geometric shape having a very special property that as you look closer and closer and closer to it, you see essentially the same thing. Now let me contrast that with the straight line. As you come closer and closer and closer, you see always the same thing. It is true. Let me contrast with a circle. From a distance, it's a circle. As you come closer and closer and closer, it becomes a straight line. It changes. And the fractal is something like coastline of a country. As you come closer and closer, you see more and more of the irregularity of the coastline, but in a kind of general way, the coastline looks very much the same, whether you look at it from a very big distance or from a rather small distance. So you see that two kinds of shapes have this property of invariance. The straight line, which we all know everything about, and some other shapes, which are like coastlines. Well, the fractals are the shapes which have this property and are not straight lines.
This computer-generated coastline is a fractal. It was created, like the Mandelbrot set, by giving a computer a set of formulae and codes that encapsulate the shape of a coastline. Remarkably, however much it is magnified, however closely you look, it always contains an identical degree of crinkliness. Many natural objects are fractal in this way. Every snowflake is different, although amazingly they all obey the same snowflake rules, variations on a six-sided theme. One of the snowflake rules is branching, a fractal process. On smaller and smaller scales, this computer crystal repeats nature's laws. Variations in those branching rules differentiate crystals from plants. As each grows, minute differences in form are magnified. The butterfly effect at work again. And yet, the most complex fractal of them all, the Mandelbrot set, obeys one of the simplest rules.
we saw this set for the first time in the middle of the night, we being my assistant, myself, and frankly, at the beginning, we thought that we are dreaming or that something had happened, a mistake had happened, because never did we expect to find this wealth of structure as a result of a formula which was of a ridiculous simplicity.
Hidden within the Mandelbrot set is all the wealth of variety that can be extracted from the equation x squared plus c. The rules of chaos govern it on an infinite scale. You could magnify it forever and never run out of detail.
It's incredibly beautiful. If you look at it, if you do computer experiments with it, if you compute blow-ups of it, you always find incredibly beautiful structures which you have not expected or even seen before. So, in other words, one might say that the Mandelbrot set is the most complicated and maybe also the most beautiful mathematical object we have ever seen.
All natural shapes are dynamic, distinct from the fixed and static geometry of man, growing and evolving over time. The unfolding patterns of nature are dictated by the ephemeral presence of chaos, of strange attractors, betrayed by the textures of bark and the branches of trees. Air currents twist water vapor into the fractal shapes of clouds. But it's one thing to generate images that resemble real objects, quite another to divine the rules that made them that way in the first place. This real fern branches repeatedly, but can we identify the rule that makes it grow in this way? This fern seems to be a perfect copy of the real thing, created by a set of rules in a computer. Again, the rules are simple and repetitive. They involve a sort of computer gymnastics called affine transformations. With them, apparently lifelike and yet wholly artificial images may be constructed. What then is an affine transformation?
If I take this picture here and I then bend it, oh, no, I know a good way to tell you. If you're watching the TV and you move to one side and look at it from here instead, look at the TV set from a different angle, you actually see an affine transformation of the image on the TV screen. It's a lot of the graphics that are used nowadays on TVs do kind of panning in pictures, squeezing out a page. There are various very simple geometrical motions of images. One was the example of a reflection, that's an affine transformation. A rotation is an affine transformation. And then rather queerer things are them. If I take a picture drawn on graph paper and then I skew one of the axes so everything suddenly becomes deformed, I just skew one axis, that's actually carried out an affine transformation. The extraordinary fact is that if you keep only the transformations and you throw away the image, you forget it, your mind is wiped clean, then you drive those transformations with a random number generator, you drive them. It turns out that always you get back the same original image that you started from.
Which is precisely how Dr. Barnsley created this computer image of a maple leaf, simply by following the maple leaf rules. But following even the simplest rules can produce an image of bewildering complexity. To play this game, the chaos game, choose 3 points and devise some rules. Rule 1, take a starting point anywhere on the screen. Rule 2, randomly choose a number from 1, 2, or 3. Rule 3, move halfway from the starting point towards the number chosen in Rule 2. So, select a starting point and run the rules. Take the new point and run the rules again, and again, and again, and again, and so on. Surprisingly, what emerges is not a filled-in triangle, but a fractal triangle. It's fractal because as we zoom into it, copies of the original are successively revealed, receding literally to infinity. In the jargon of chaos, this curious triangle is the attractor for those simple rules. It's a new mathematics which sheds light on the old and intransigent problems of physics, problems such as turbulence. In a slowly flowing stream, the eddies and tiny whirlpools die out almost as soon as they form. But as the stream quickens, the eddies live longer, until a moment comes when the turbulence grows, building upon itself to produce a flow that swirls and tumbles wildly. Disturbingly, turbulence seemed to rear its head wherever scientists looked, although little was known of how it occurred. For decades, the theories proposed by the Russian physicist Lev Landau seemed the closest to providing the answer.